thank you very much for the invitation. I'm very pleased to be here in Rome. I started with this slide to make it a little bit more dramatic, I think, about the topic I'm going to talk about. It's about the hothouse climates of the Paleocene and Eocene, when the temperatures were much higher than today, but maybe something we are going to face in the future. Just touch, yeah? So, well, yesterday everything was in Italian, so I was just sitting here and looking at in this room, and I thought, okay, there's some nice paintings here, which quite nicely, let's say, summarizes a little bit the talk I will be giving, but also the talks that we have seen this morning. So it's a little bit of astronomy involved, there's a little bit of chemistry involved, and also some marine expeditions. So I thought it's a nice start to introduce the talk. Okay, so I guess most of you are familiar with this cartoon, which was made in a compilation paper by Thomas Westerholt in 2020, which nicely summarizes actually how the climate evolved, the global temperatures, or the anomaly of the temperatures with respect to pre-industrial values over time. And is there a pointer which I could, no, there's no pointer. I can use this, I guess. No, I can also not use that, so I would just talk. Is there, I turn it on. Oh, but you cannot see it, I think, anyway. Okay, it doesn't matter so much. So what you see here, so we had a very nice talks this morning also about the Quaternary, so the icehouse world, let's say the past millions of years or 2 millions of years. But you can also, so these are the time interval where the CO2 concentrations were actually quite low, much lower than at present, you all know that. And on the right side you see these projections by the IPCC for the future. So we have these different scenarios. One is the most optimistic one is the Paris Agreement, where the temperatures will not rise too much and hopefully they will decline in the future. But we also have these very pessimistic scenarios, so where the CO2 will increase and also the global temperatures will increase. And so in this pessimistic scenarios, the temperatures can rise to, let's say, more than to 15 degrees Celsius or something like that. That looks very dramatic, and maybe we already face today, let's say, these changes. So when you want to study what is the effect of maybe how the future climate will look like, so we may transition actually to a complete, let's say, different climate state as what we have seen, let's say, so far. So therefore, it is very important to also study, and we can study those time intervals in the past where the temperatures were actually much higher. And so, no, I have to go that direction. So I want to take you down to this hothouse world or warmhouse world, somewhere in the Paleocene, Eocene, starting around 60 million years, ending around 42 million years. And the temperatures, what you can see there, also reached, according to this reconstruction, up to 15 degrees Celsius. And this record is actually based on the so-called benthic isotope records obtained from the open ocean. So I just want to go a little bit back in history. So where does this series actually come from? They come actually from two expeditions. One was Schatzky Rise, 1209. And the other one came from sites drilled during LEC 208, and I was very lucky that I could attend this expedition here. So you will see some familiar faces, I guess, in some of the pictures I will show. So this is Dick Krohn. He unfortunately also passed away much too young, and Jim Zackles, and also on the back here you see Appie Sluis, who was really young at that time. And this expedition started in 2003. We traveled from Rio de Janeiro all across the Atlantic Ocean to the Walvis Ridge site. And there we drilled. We started with drilling 1262. That was the deepest side of the expedition. Here you see the seismic profiles, and you could already nicely see in the reflectors what we thought was the so-called Paleocene-Eocene boundary, where we expect that, and the KP boundary, so the Cretaceous Paleogene transition. So what I would like to show you also here is that I think now with IUDP, it was a very important program so that we can actually cover sediments continuously, also in the older records. And that means that we can also study climate change on the same scale as what most of people have been doing, working on in the Quaternary. So on a precession scale, we can actually resolve, let's say, how the climate has fluctuated. And important for that is that multiple holes should be drilled at one location. So to be sure is that the core gaps you have are covered, let's say, by the parallel holes. And that's shown in this diagram. So this is just the magnetic susceptibility measurements of 3 holes which were drilled at this site. And that enabled us to, let's say, to make a nice splice record of this site, and where you can recognize already some characteristic transitions, like the Oligocene-Eocene boundary, for instance, the Eocene-Paleocene, which steps out also as a sharp, let's say, increase in the magnetic susceptibility values, and also the KT boundary was there at the bottom. So we had a complete recovery of the whole Paleocene and the early Eocene. And here you see 2 pictures of that during the expedition. So that's Casey Lohman there sampling the KT boundary, and this is Jim, and on the back you can recognize Isabella is there, where we got the first copy of the PTM. So that is marked by this very nice clay layer. So the carbonate, so most of the sediments are 95–96% of calcium carbonate. And then at this PTM you see is that all this carbonate has been dissolved, and you only see the appearance of this clay layer. So we were very happy to get a nice copy of this PTM. We drilled more sites. I just want to show you another example. That's the shallowest site we drilled, or in terms of paleo depth, water depth. That was 1263, shown over there. So the nice thing of 1263 is that the neogene part was relatively thin. So we drilled that also at 1264. So we started almost at the Oligocene, actually the Oligocene-Eocene transition very closely, and then we drilled all the way down here to the Paleocene-Eocene boundary. And that was important because this site has the highest sedimentation rate. So if you want to core it by APC drilling, it was one of the only opportunity to actually drill it at that location at this relatively shallow water depth. So this resulted in this nice paper which of Jim. So let's say the main result of the expedition is that so we had 5 copies of the PTM at a different water depth, and they all showed very nicely this drop in calcium carbonate at the base, and then it remained low, and then you start the recovery at the end of the PETM for the different sites. So this is the calcium carbonate content, and then you can place everything on a common time scale or a depth scale using the carbon isotopes values of the bulk of the sediment. And then what you can see very nicely is that at the base of the PETM, so you see this very sharp transition that occurs at the same time. But then you can see is that the shallowest site, that the calcium carbonate starts to increase already after maybe 10 or 20,000 of years or so, and that the deepest site, 1262, it takes, according to this age model, 80,000 years or so before it starts to recover to normal values. And so the idea behind this is that what are we looking at here is we are looking, this is the depth transect. No, I'm going the wrong direction now. So what are we actually looking here? We are looking at a carbon, so a light carbon source, so an injection of light carbon into the ocean atmosphere system, which has an average composition in the deep ocean of -3 per mil, this carbon isotope excursion. And that causes the calcite compensation depth to rise in the ocean. You get dissolution of calcium carbonate, and then it takes so much time that the CCD starts to decline again. So the main theory behind this is that, okay, we have warm climates at that time, and so probably at this point, you cross a tipping point or a threshold in the climate system, and you get a release of a light carbon source. And the general thinking is that it has to do something with methane, which is in the ocean in terms of clathrates, which come free. They oxidize, they give this light carbon isotope excursion, and they cause an amplifier of the global warming, which is already warm at that time. Another nice result of the expedition was if you go a little bit higher in the course, you see another red layer. We called it the Elmo horizon, or later on it was more officially called the Eocene thermal maximum 2. And we studied this because it was interesting, because we could find it in all the other sites which we also drilled. And if you look above, let's say, the Elmo, there's another brown layer, and even in the top you see another layer. If you look at this Elmo horizon, it showed very similar characteristics as that of the PETM, but almost half in scale, let's say, of the transition you see at the PETM. So we also see a drop in calcium carbonate, but it doesn't go back to 0%. There is still in the order of 20 to 40% of calcium carbonate left. And it's also marked by this drop in the delta C13 composition of the carbonate. But the excursion is also half, let's say, of that what you see during the PETM. So after this, we performed high-resolution isotope studies. That's the work from Head McCarran, for instance, for the PETM. Lucy Stubb as a PhD, she worked on the Elmo and H2. And then Kate Littler, she did the identic isotopes of the interval of the Paleocene and the early Eocene. And then Vittoria Laurentano, one of the PhDs, also she finished these analyses all along the eco. And so this is just to indicate where the different positions is. So you see the PTM is characterized by a very sharp decline in both the carbon isotopes as well as the benthic oxygen isotopes. So giving that you have a light source and then a warming of the deep ocean during that time interval. That's the position of the Elmo, so Eocene thermal maximum 2. This is the position of the eco. There is also a transition in the carbon isotopes. It's called the early Eocene carbon shift, which is also very characteristic and also in other areas. So in the green line, what you also see there is the record produced by Thomas Westerholt that was from the Pacific Ocean, which actually mimics the pattern you see here at the Walvis Ridge. And these two records were actually used in the Xenogrid record, which I showed you before. But if you look then in detail, you see more of those excursion values, which were termed by Benjamin Kramer already just before we went on this expedition. So it goes from H2 to W. And so you can see is that during this time interval, the climate was far off stable. We see these prominent changes in the carbon cycle and the temperature response. And that is also very nicely reflected if you just plot regression coefficients or regression lines between the calcium, the delta C13 and delta 18O. They all show the same relationships. So notwithstanding of the amplitude, the relationship are always the same. So it seems that there's a strong connection between these perturbations in the carbon cycle and, let's say, the temperature response in the deep ocean. I think that's a very important message I also want to tell you here. So notwithstanding that there are no ice sheets at that time, but still you see is that the climate is very invariable, let's say, of these type of variations in a warm climate. Oops, that goes a little bit too fast. So after many studies have been done, I just show you a couple of this, Benjamin Harper and Jim Zeckels. So Jim measured the magnesium calcium as a proxy for changes in the surface temperatures of the ocean of the PETM, so both at the Shatsky Rise as well as at the Walvis Ridge, and he came up with an increase of temperature during this event of 4 to 6 degrees. And then during the Elmo or ETM2, we find a temperature rise in the order of 2 to 4 degrees Celsius. Right. So now a little bit about the orbit. So another thing what became interesting, okay, what causes then these perturbations which we see in this time interval? And so using just the color reflectance record you see here on the bottom and the magnetic susceptibility for the interval between the PTM and the Elmo, you can clearly recognize these long-term modulations, 1 to 5, which we can relate to changes in the eccentricity or the 405 kiloyear component. And then you can also see the shorter term variability, which I numbered here 1 to 19, which you can relate to the 100,000 year cycles of eccentricity. And you can also recognize this in other sites. So then you can make a first age model based on tuning this to the at that time available orbital solutions. So this was at that time there was only the Lascar 2004 solution and that of Ferrari, the R7 compilation. And I just show you here two options of how you could actually tune this time interval. So I use the 405,000 year of eccentricity as a first order approximation, and then I tune the individual, let's say 100 kiloyear cycles of this. And another assumption what I made in this case is that, let's say, the onset of the PTM should just follow, what you see here on the bottom is these long-term modulations of eccentricity around 2.25 million years. And so with the idea behind this is that when you go from an interval where you have these minimum in this long-term modulation, that when you get out of this, that you reach a tipping point to, let's say, actually activate these methane clathrates to escape from their reservoirs. So these are these two options. And according to these options at that time, what we proposed is that both the start of the PTM as well as the start of the ETM2 occurs in a 400,000 year and a 100 kiloyear eccentricity maximum. This was evaluated shortly after by Thomas Westerholt, where he applied then different records, but from the same, let's say, composite. So he used the A-star record and the iron record, and he made a similar interpretation. He recognized the same amount of 400 kiloyear cycles. And then also most of the 100 kiloyear cycles are the same as what we recognize based on the other proxies, except, let's say, between 14 and 12, cycles number 14 and 12 numbered by him, he recognized one cycle less in this particular interval. So why is that so important? Well, that's important because if you then go to tune this, then according to this recognition of the amount of cycles, it means that the ELMO should not be in a 400,000 year eccentricity maximum as forcing, as well as that the base of the PTM should not be in eccentricity 400 maximum. Yeah, it should be shifted because he considers less time within this particular interval. We showed two options here. So one shifting everything 400,000 years older. So this is more or less that was the status in 2017. So the option I showed here was shown here in pink. And then the option 2 in Sinogrid is actually more or less the same one as that option shown here. But that was tuned not to the Lascar 2004 solution, but in the meantime, Jacques Lascar has also calculated new solutions, and the 2010B solution fitted also quite nicely with the data. So that's the one he used in this paper in 2017, and that was also the basis of the Sinogrid. So now if you look at all the other hyperthermals, what you can see actually is that all these hyperthermals, they fit very nicely within this eccentricity maximum, except the PTM. Now, because according to this H model, it should fit somewhere at, let's say, the transition from an eccentricity maximum to a minimum. And that's a little bit strange. So it gives then still the PTM some kind of an exceptional, let's say, as something special. It is a special event because the amplitude is so large, but also in case of that, its phasing with the orbits is different, could make it an exception, let's say, and then you could think about other triggers like volcanism, for instance, for this event. So Richard Seeby and Richard Seeby was also working on new astronomical solutions, and then we thought, okay, we had a meeting in London, Royal Society meeting, where we discussed this again and to see, okay, how can we evaluate again, let's say, using new astronomical calculations, which he did for this time interval, to look at the phasing again. So that's what is shown here in this paper. So what we did here is we fixed, let's say, we took 2 points, let's say the start of the PTM and the end of the major excursion, and then we just tuned the lower part of the record and the upper part, and searching for the best fit with the orbital calculations. And we did that for several orbital calculations, which he made, but also from that of the Jacques Lascar. And this record, what you see here, gave us the best fit with the data, with the filters we obtained. So the solution That was not a surprise. That was a solution which Richard made, the CB 2018A solution, which showed the best correlation, in fact, with the data. So according to this, you can recognize again these 19 cycles. And in particular here, this is the complicated interval where we have discussion with Thomas, the 678. You can already see that in that particular interval, the eccentricity cycle, in particular 100 kiloyear, is not very prominent. Yeah? So that is open for different interpretations. But in this solution, you can recognize actually 6, 7, and 8. It also implies is that the duration of the PETM is approximately 170,000 years, plus or minus 30 kiloyears. And it also implies is that PETM most likely covers 2 eccentricities. Yeah? Another implication is, because this gives the best fit, let's say, with the astronomical solution, there you see, let's say, the different astronomical solutions we tested. So the root mean square deviation is the smallest for the ZB solution between the filter and the original, let's say, calculations. So if that is the best solution you could apply for this interval, this solution shows what we call a resonance transition between 40 and 50 million years ago. So that means that one of the components of the S4 minus S3 terms, so that are the main circular resonances of the solar system, and that of the G4 and the G3 terms, are changing their period. So they actually go from this very stable 2.4 million year cyclicity, they go back to 2 million years. Yeah? And here you are actually in the transition. So that's also interesting for astronomers that something may occur there at that particular time interval. So we came up with a new, H's then for the ELMO and for the PTM, the base, which are much more consistent with my, let's say, my original tuning of these record of 2 million years between those two starting points of these events. Okay, now let's go back to Italy. And so, because here you also have very nice successions in the Marche region. For instance, here, this is the Contessa Road, close to Gubbio, where you can see nicely the outcrop of the PTM, and you can already see that there are 2 clay layers in that layer. And also that behind the shed you can also find the ETN2 and H2 events. So this is a place where we always go to with the student during the Urbino Summer School. And there was a paper by Victor, I think 2022, where he looked at these 2 clay layers, and actually what you can conclude also from his study is that there is good evidence that the PTM actually consists of 2 eccentricity maxima in there. Yeah? Then if you go to the Botticcione section, so you get a little bit upward, so you can also get some very nice food over there. Then you see the nice outcrop with the eco, and also with the nice red clay layers in there, and which you can study. And that's what we wanted to do many years ago, but then there was another section, was a suggestion for the so-called Smira section, which is nearby, so very close to Cagli, in that area, where all the, let's say, all the layers are more or less horizontal. So we thought, okay, that's an excellent location just to start drilling. So we went there, so we had our own small ICDP project at that time to drill a hole with this company from Milan, together with Simone Gagliotti. I think most of you also know him. And so we obtained very nice cores through this quarry, and we actually moved also the drilling equipment downwards to get further back into the Katy boundary. But then, yeah, the weather changed also in Italy. So it became much colder and a lot of snow, actually. So yeah, it was a harsh time. No, it was a very nice time to do this drilling, and we obtained very nice cores from Smira. And you can also see this a transparent liner that you can see all these nice cycles already in the core barrels itself. But it is quite hard material, so we had to go to the NEOS in this case to cut, let's say, all these cores in 2 halves. And unfortunately, this is the PTM succession. You can see it's very thin, so this part has been slided more or less in this area. So it's not very useful for studying the PETM in this succession over here. But if you look at the ETM2, H2 interval, so we measured the bulk carbon isotopes, which you see here on the left. So you see again this very nice excursion during ETM2 and then also during H2. But here we see very nicely the imprint of the individual precession cycles during this particular interval. So let's take the LASCAR 2010 solution with the calculated precession cycles, and then actually it's not that difficult to count the number of precession cycles, let's say, between those two events. And so I think this is also this is not published, but it just shows you something interesting also. You can really see that it is very asymmetric. You see, very steep onset of the carbon perturbation, and then you get a recovery phase, and then you jump into the next 100 kilometers. It doesn't just remind you of the glacier-interglacier variations sometimes you look at, and the quaternary. So there are no ice sheets here, but apparently the climate system already gives some asymmetry, let's say, in the carbon perturbations. So I think that's something to be, let's say, aware of, let's say, of how the climate system may work already, let's say, in a greenhouse world. So I just yeah, you can count how much time is in there and how much time it takes to recover. Another very famous succession, and that is also nice to address, are these continental successions, which are found in, for instance, in the Bighorn Basin, which have been studied very intensively, and shown here, for instance, is one of the studies of Gabe Bowen, of Polcott Bench, which contains the PTM, very nicely is represented by the CIE again, based on these carbonate nodules which they have measured. And then they can also recognize these different soils, alterations, and they can make a time scale of that. It was shown here. This is also published by Thomas Westerholt in Climate Past 2018. Where you see these precession cycles within, let's say, and the correlation to the marine record of this Polcott Bench record, which was actually the number of cycles is very similar as the one which Heva Abdulaziz already showed previously about the number of cycles. But on the basis of this continental succession, they arrive at 120 kiloyears of the PTM, where we arrive at what I showed you before, 170 kiloyears. So there is still a discrepancy of how much time is actually within the PTM. It's always open for discussion. If you go in the same area, but a little bit higher in the succession, in the upper Deer Creek, and that's a part where Hemmo Abels also have worked a lot, you will find also very nicely these fluvial deposits and overbank deposits and soil formation. You also have those purple zones. You also measure, let's say, the carbon isotopes of the carbonate nodules. Then you can nicely recognize ETM2 and H2 in that in particular interval. And those, and you can start, okay, let's try to correlate those to the SMIRA section. And then it appears already difficult because then it seems, so if you use the base of the ETM, so the carbon isotope excursion of ETM2 and H2 as tie lines, then we find one more precession cycle in SMIRA than in the Bighorn Basin. And so most likely these continental succession may not be complete, or maybe you have intervals where you have very low sedimentation, and that can have implications, of course, if you want to let's say estimate the duration of these type of events. Okay, so this is I just only have a few slides more, so I just want to show a little bit of the work we are also doing now in the last years. And that's so far you have seen a lot of oxygen isotope records, so based on the very classical method. And so you all know is that, okay, there are some issues with the oxygen isotopes because it's not only reflecting temperature, it also reflects a change in the composition of the water, the isotope composition. It can be pH effects, it can be some phyto effects, and these kind of things. So, and So one of the recent developments is to start to measure the so-called clumped isotopes, so the delta 47, let's say, of these. And now, with the new techniques and the precision of the instruments, we are able to measure these forums also, which was not possible in the past. So what does it actually say, clumped isotopes? Well, it actually measures the mass 47, so the combination of the heavy elements, C13 and O18, with respect to the light molecules. And what we think is that this fractionation is mainly caused by changes in the temperature. Maybe there's a small pH effect, but so far there's no indication that that plays a role. One of the disadvantages of this method is, so if you just look at this plot, so this is a high accuracy, high precision example, low accuracy, high precision. And then the clumped isotopes are actually here in a high accuracy but very low precision measurement. So what that means is you have to run a lot of replicates to get a good value. And unfortunately, I had a very good student working on this, so he measured a lot. And actually, he started to remeasure all the data we had from what Lucy did in the past on ETN2 and H2. So he had measured it again, because unfortunately at that time we didn't have this machine. And so the normal isotopes mimics more or less is what we knew before. So that was okay. That's good to see. And then what we did is we actually binned the data in several intervals, just because to combine all these replicate analysis. So we had what we call background state, slope state, and then the hydrothermal peak. And so we identified, let's say, 3 bins based on the oxygen isotope intervals. Yeah? So what you can see now is that, so with this line, what you see here over there, that is the oxygen isotope calibration to temperature in a greenhouse world. So we just assume is, let's say, the oxygen isotope of the oceans is something like -2 per mil or something. Yeah? It's the same equilibrium, the same line as what was used in the Westerholt compilation figure I showed in green. And what you can see now is that the clumped isotope values are all higher in temperature than based on the traditional oxygen isotope record. Right? It's more than 2 degrees, maybe 3 degrees in average. The nice thing is that you can see that the temperature increased during the hydrothermal. It's also based on the clumped isotopes. So that's very promising that this technique works. But that implies that if you use the clumped isotopes in the temperature calibration of the oxygen isotopes, that the delta 80 of the water should be much heavier than what we generally assume, let's say, in our computations. Yeah? Or is there something else going wrong? Because there is we don't expect to have ice on the world, let's say, when there is plus 15 degrees Celsius on the global scale. Or maybe there's groundwater reservoirs we don't know, or there are big lakes at that time. You know, there are all, of course, uncertainties. But what we do think maybe is that the pH effect of benthic isotopes is much more important sometimes than we think it is. Now I just go to one of my last slides. So this is the compilation which you see in the Westerholt grid, with the deep sea temperatures. And so we go up to, let's say, 14 degrees Celsius during the eco. And now Tobias has also measured, and I was very happy that he sent me this graph. These are all the clumped isotope measurements now for this particular time interval. So you can see, so this not only this, so in red, this is the one which were based on the South Atlantic, so the Walvis Ridge material. But the blue ones, they are based on the North Atlantic from Nele Meckler, her group. She also has measured, so independently, the clumped isotopes of this interval. And you can see that during the eco, temperatures may have been as large as bottom water temperatures up to 22 degrees Celsius. It's scary, isn't it? Because if we think that the PCO2 conditions at that time were just 1100 ppm or something like that, maybe sometimes a little bit higher. That the climate sensitivity is much stronger, much steeper than we think it is. And what is now used, let's say, in a lot of climate models. So I think this is very important to see if we can, let's say, confirm these higher temperatures, let's say, also with climate model simulations. And I know there are indications for that. So when you take into account, let's say, the micro mechanisms of the droplets and these kind of things, that the sensitivity might be much higher, let's say, than what we actually think it is. So that's just what I wanted to finish with. So some conclusions. So I think there's a new absolute chronology for the Paleocene-Eocene boundary that requires a transition in the solar system fundamental frequencies. PETM onset occurred near, what I believe still 405 kVA eccentricity maximum, suggesting an orbital trigger. So there's still a lot of discussion, of course, if there's a volcanic trigger, let's say, for this event. The duration, I think, is much longer than we presently assume. And then I think also the clumped isotopes, that open a new, let's say, dimension, I think, to the stable isotopes that we are looking at present. It may also have implications maybe for sea level reconstructions you do in the Quaternary. Because if the isotope of the traditional benthic is not only, let's say, temperature and and ice volume, but also pH, so you have to look at that maybe also a little bit about those uncertainties. I think that's more or less what I wanted to tell. Thank you very much.